exponent is a little floating number at the top. I'm sure you've seen it in a lot of places, you just didn't realize it. You thought maybe the person wrote the number too small or wrote it crooked or something, but in fact that little floating number at the top is actually called an exponent, and we do something special with it. The exponent tells you how many times to multiply the number by itself. So an example of 3 to the second power, that would be 9. So 2 is called the exponent, and 3 is called the base. And the base is what's multiplied. The exponent is how many times you're timesing it. So it kind of looks like this. 3 times 3 is 9. And that's twice that I multiplied it by itself to get 9. So then 3 to the fourth power is 81, because 3 times 3 times 3 times 3 is 81. I timesed it by itself 4 times. So let's practice with some smaller, easier numbers, like 1. 1 to the second power is 1, because 1 times 1 is 1. In fact, 1 to any power is 1. 4 to the second power is 16, because 4 times 4 is 16. Now 10s are real easy, because 10 to the second power is 100. And honestly, I'm going to show you a little trick about 10s later. You really don't even have to multiply. You just have to count zeros. So let's look real quick at the multiplication chart, and you can probably notice a pattern with these square numbers. So let's just start with the first one. 1 squared is 1. And there it is. 2 to the second power is 4. And there it is. Do you see a pattern emerging? 3 to the second power is 9. 4 to the second power is 16. 5 to the second power is 25. And 6 squared is 36. And 7 squared is 49. And 8 squared is 64. The pattern is really emerging now. So let me ask you, what is 17 squared? If you answered 289, then you followed the pattern perfectly. There's another very interesting pattern with these exponents when we talk about patterns with 10. So here we go. The second power of 10 is 100. Look at the pattern of zeros and tell me what you notice. So now 10 to the 6th. What about 10 to the 15th? So the patterns with 10s are in fact quite easy because you're really not doing any math but counting zeros. Now the pattern with decimals gets a little trickier. So check this out on the patterns with decimals. When I give you the word 100, you don't see a decimal, do you? But if I asked you to write 100 in dollar form, like when you're counting money, you would immediately know where that decimal goes. To write 100, like dollars, you would write it like this. And there's the decimal. In fact, in America, since we have pennies and we go to the hundredth of a dollar, we have 2 spaces after the decimal when we talk with money. But other countries only have 1 space after the decimal with money, or 5 spaces after the decimal. So it kind of depends on what money you're using is how many zeros you need when you're talking about money. But when we're talking about science, we can in fact have as many zeros as we want. Scientists call these zeros insignificant digits because I read this number as 314. I don't really have to read all those zeros if they're not having to do with the scientific experiment I'm doing right now. But I write them there to show people how precise I am, how accurate I am, and maybe I need them later for dividing something. Right now they're just called insignificant, and they help me move the decimal to the right spot. So let's look at another example. If I give you this big long number, I could simply write it as 4 times 10 to the 5th power. Because the digits are still 4, the question is how many times did I multiply it by 10? If I add the decimal would originally be here after the 4. But I've moved it 5 spots. 1, 2, 3, 4, 5. There it is. Now if I'm talking about patterns with decimals and I add something that's a little trickier of a decimal, like 4.1 times 10 to the 5th, I'm going to end up with 41, since I'm still using the same digits, 4 and 1, and I've just moved that decimal over 5 spaces, like this. So the patterns with tens and the patterns with decimals are actually kind of easy. And that's one of the reasons that scientists use them all the time. Scientists have a real big problem if they're talking about outer space and they're talking about millions of billions and trillions and quadrillions of miles away. They're not going to sit around writing that many zeros down on something. And another kind of scientists, you know, the ones that work with microscopes and stuff, they're using microscopic stuff. And they're not going to sit around and write 0.000000001 of an inch, right? They need a better way to write very large numbers and very small numbers. So they have this thing called scientific notation. So if I just take a big giant number like this, I can write it in scientific notation like this. So I get the same digits, 5, 8, and 9, and I take all those zeros and I just write it as a 10 power. In this case, 10 to the 12th power. So let's practice on a few. 620 times 10 to the second power. I'd have 620 because that's the same digits. But now, how many zeros do I add? In this case, 2. 10 to the second power means I add two zeros. Let's try another one. 3.14 times 10 to the second power. So I know I'm going to have a 3 and a 1 and a 4 in my answer, but now I need to find where the decimal is and move it 2 spots. So my answer is 314. So 3.14 times 10 to the second power is 314. One more for funsies. So 2.3 times 10 to the second power. I know I'm going to end up with 23. But when I throw in that decimal, I know I have to move it 2 spots. There's no place to move it. So let's give that a try. So I add all these insignificant zeros, so it's a lot easier to move the decimal. So the decimal started off between the 2 and the 3. Now I need to move it 2 spots. 1, 2. And I can just get rid of all those other zeros. Okay? So now you know a little bit how to do scientific notation, a little bit about exponents, a little bit about powers of 10. But if you noticed in this video, I did something kind of weird. In this video so far, sometimes I would say 10 squared, 3 squared, 4 squared, and sometimes I would say to the power of 2. 3 to the second power is 9. Or I could say 3 squared is 9. So the question is, what is a square number? And let's just take it number by number. Let's just start with the number 1. Is 1 a square number? Let's see, this side measures 1, and this side measures 1. So 1 is a square number. Okay, let's try 2. Is 2 a square number? So if I get 1, 2 things, and I line them up, then I put 1 on this side and 2 on this side. I cannot make a square with 2. I'd make a rectangle. So is 2 a square number? Nope. Let's just try another number, 6. Is 6 a square number? So I get 1, 2, 3, 4, 5, 6. Could I rearrange these to make a square? If I put this one here, does that make a square? Nope, that's a rectangle. Let's get a little deeper. Is 5 a square number? Can I put this square somewhere else that would still keep the design a square? Nope. So 5 is not a square number. So some numbers are square and they can be 2-dimensional. And some numbers are cubed and they can be 3-dimensional. And some math that you're going to learn is honestly beyond the physical world. When we're talking about 4th-dimensional things, you're going to get in an argument with a bunch of scientists about whether that's real or not, or whether it just only applies to black holes. For now, you only need to worry about 2-dimensional numbers and 3-dimensional numbers. And that's it for exponents today. Just remember that exponents means how many times you times it. And seriously, take my advice, use a calculator. I can only do square numbers in my head up to like 12. If you ask me 6 to the 4th power, I'm going to need a calculator to get it. So seriously, use a calculator. And I also taught you a little bit about hidden decimals and multiplying by 10 and scientific notation. And there you have it, exponents in a nutshell.